In this video, I'm going to go over how to graph a logarithmic function. Before I graph a log function, I want to start by looking at the exponential function 2 raised to the power of x. I'm going to plug in a few values for x and then plot those points. So if we plug in -2, we get 2 to the -2, which is 1 over 2 squared, which is 1/4. If we plug in -1, we get 2 to the -1, which is 1 over 2. 2 to the 0 gives us 1, 2 to the 1 gives us 2, and finally 2 squared is equal to 4. So we end up with the following ordered pairs. And now let's plot those points and then connect them to get our graph, which should be a curve that looks like this. One thing to keep in mind with exponential functions is that there is a horizontal asymptote. For this one, there's a horizontal asymptote at the line y is equal to 0. And that's because on the left side in particular, the graph keeps getting smaller and smaller, closer to 0, but never actually hitting 0. We use asymptotes to indicate these kind of boundaries. For the log function, to get the ordered pairs, we're going to use the fact that log of 2 of x is an inverse function to 2 to the x. And with inverse functions, there's a switching of the x and y values. So since we have the ordered pairs for 2 to the x, all we need to do to get the ordered pairs for log base 2 to the x is switch the x and y values. We end up with these 5 ordered pairs. If we plot them, connect them to get our graph, we should have something that looks like this. Now, since the exponential function had a horizontal asymptote at y is equal to 0, if we switch the x and y values here, because they're inverses, we actually end up with a vertical asymptote at x is equal to 0. Now let's look at our first example. Let's say we want to graph f of x is equal to log base 3 of x. I'm going to start by writing it as y is equal to log base 3 of x, and then rewrite in exponential form, which gives us 3 to the y is equal to x. Just like the last problem, I'm going to plug in different values for the exponent, which in this case is y. So I'm going to plug in y is equal to -1, 0, and 1. 3 to the -1, which is 1/3, which is our x value. 3 to the 0, which is 1, which is our other x value. And then finally 3 to the 1, which is 3. So that's our third x value. And if we plot our points, we should see a graph that looks very similar to the previous graph. And there's still a vertical asymptote at x is equal to 0. Now let's try the graph of f of x is equal to log base 3 of x plus 4. I've got all the information on the left from our previous example because we're going to use that to graph this function. So first thing is, if you recognize the base function of log base 3 of x, we know that we can start with those same ordered pairs because we've already done the process of converting it to an exponential to get those ordered pairs. And after that, we can use transformations. So plus 4 at the end means that the graph is going to shift up 4 units. And this means to get our new ordered pairs, we need to add 4 to all the y values. This gives us 1 over 3, 3, 1, 4, and 3, 5. Notice that all the x values have remained the same. It's only the y values that have changed. And now we're going to go ahead and plot these points. And before we do that, I just want us to recognize that we should end up with a graph that's just shifted up 4 units from our original graph. And again, the vertical asymptote still remains at x is equal to 0. If you shift a graph up or down, it does not change the vertical asymptote. Let's say we want to graph f of x is equal to log base 3 of x plus 4. Again, we want to recognize that the base function is log base 3 of x. Now using transformations, the x plus 4 in parentheses means that it's going to affect the x values. When we're dealing with the x values, it's sort of opposite of what you would think it should be. So the plus 4 actually indicates that it's a shift to the left. And to get our new x values, we're actually going to subtract 4 from all of the x values, keeping the y values the same. Subtracting 4 from the first ordered pair gives us -11/3, -1. I'm going to rewrite that as a mixed number so it's just easier to plot. Our second point becomes -3, 0, and our last point becomes -1, 1. So we have our 3 points. Again, before I plot them, we just kind of want to keep in mind that we should end up with a graph that looks just like our original but shifted to the left 4 units. In this case, whenever there is a left or a right shift, the vertical asymptote will change. So vertical asymptote at 0, if we shift that to the left 4 units, does become a vertical asymptote at the line x is equal to -4. All right, on to our final example. Now we're going to graph f of x is equal to -log base 3 of x minus 2 plus 1. Still working with a log base 3 graph. So we're going to use the same 3 ordered pairs. And there's going to be 3 transformations that occur for this graph. The x minus 2 in parentheses means that there's going to be a shift to the right 2. The plus 1 on the outside means it's going to shift up 1. And the negative in the front indicates that there's a flip along the x-axis. And I'm going to start by applying the flip first. To apply the flip along the x-axis, we can change the signs of all the y values. The x values remain the same, and the y's become a +1, 0, and then a -1. And if we look at the graph, after we plot those points, we should see it looks the exact same as the original graph, it's just been flipped along the x-axis. Now let's apply the second transformation, which is a shift to the right 2 units. This means we have to add 2 to all the x values. And again, if we graph it, we should see it's the same as that green graph that we had, just shifted to the right 2 units. Remember, a shift left or right does affect the vertical asymptote. So in this case, the vertical asymptote changes from x equals 0 to x equals 2. And now finally, we're going to apply the third transformation, the +1. So to shift the graph up 1 unit, we're going to add 1 to all the y values. And so we end up with our final 3 ordered pairs. So let's plot those points, keeping in mind that the vertical asymptote is now at x is equal to 2. And then we can finish our graph by connecting our points. In summary, when you are trying to graph a log function, you want to keep in mind the exponential equivalent. And that can give you your starting ordered pairs, and after that, you can always use transformations to graph a more complicated log function. I hope this helps.